Hello class, and welcome to our next video lesson on solutions. In this particular video lesson, we're going to talk a lot about, first of all, how solutions are made. We'll also talk about different properties of solutions. Solutions are all around us. As you can see in this picture, these are just a few different examples of solutions that we use on a daily basis. But let's get into talking about what solutions are. First of all, we've got to backtrack a little bit before we get to talking about solutions specifically. First of all, let's talk about a substance. When you think about pure water, no matter what you do to it physically, freeze it, boil it, stir it, or strain it, it's still water. On the other hand, if you boil salt water, the water turns to gas and leaves the salt behind. So how does chemistry explain these differences between pure water versus salt water? Well, let's talk about a substance first. A substance is matter that has the same fixed composition and properties. And remember, composition is how something is made. What is it made of? So matter that has a fixed composition is what we would call a substance, or sometimes referred to as a pure substance. It can't be broken down into simpler parts by ordinary physical processes, such as boiling, grinding, or filtering. In order to break down a substance, it's going to take some type of chemical process in order to break it down. Only a chemical process can change a substance into one or more new substances. And it shows you here in this box some different physical processes and some chemical processes. In order to change or break down a substance, you would have to take that substance through a chemical process. Elements and compounds are examples of what we would call a substance or a pure substance. An element, it can't be broken down into a simpler substance. It is just simply one type of atom. And we find these, of course, on the periodic table. A compound, however, which is what we refer to as water. Water would not be an element. Water would be a compound. A compound is made up of two or more elements that are chemically combined. Now, you can break a compound down, but since they're chemically combined, it's going to take more energy, and you would have to use one of those chemical processes that we saw on the previous slide in order to break a compound down, okay? But these are two examples of a substance, all right? It's not that easy to break them down. It takes a whole lot more energy. It takes chemical processes, all right? Now, let's talk about the flip side of that, which is a mixture. Matter can also be categorized as a mixture. Mixtures are a combination of substances that are not bonded together, and they can be separated by those physical processes that we saw on the previous slide. So let's backtrack for just a moment. Matter can either be a substance or a mixture. Substances, such as compounds, you can break down, but it takes a chemical process to break them down. Mixtures, for example, they are not bonded together chemically, so they can be easily separated by using some type of physical process. Now, unlike compounds, mixtures do not always contain the same proportions of the substances that they are composed of. So remember we said that a compound has the same composition throughout, as well as an element. That means they are composed of the same thing. Mixtures are not. Mixtures are a combination of different substances that come together, but they don't bond. Mixtures can also be broken down into two different types. They can either be homogeneous or heterogeneous. Now, a heterogeneous mixture is a type of mixture where the substances are not mixed evenly. This would be a type of mixture that has bigger parts that you can actually and physically see. For example, this watermelon and seeds, we would consider that a heterogeneous mixture because I can see the red watermelon part of it. I can also see the seeds. And then you also have the outer green part of the watermelon as well. Now, a homogeneous mixture, on the flip side, it contains two or more substances that are evenly mixed on a molecular level, but they're not bonded together. So with a homogeneous mixture, sometimes it's hard for us to tell that it's actually a mixture because you can't physically see the different parts that make up this mixture. They're more evenly distributed throughout. And another name for a homogeneous mixture is a solution. So when we refer to solutions, we are talking about a homogeneous mixture, okay? And milk would be an example of such type of mixture. Now, let's get more into talking about solutions. Now that we've kind of built up some background knowledge about a pure substance, a mixture, we've talked about different types of mixtures. We now know that compounds are chemically combined, and it's harder to break them down. Mixtures are physically combined, and it's much easier to separate them, okay? So now let's talk about how solutions are formed. A substance, first of all, when you make a solution, you've got to have a solute or a solvent. Now, a substance that dissolves or seems to disappear is called the solute. A solute is something like, for example, salt. If I'm trying to make salt water, then my solute is going to be my salt. The substance that dissolves the solute is called the solvent. So in that situation with the salt water, my water would be the solvent. Okay, so these are the two components that you have to have in order to make a solution. In a hummingbird feeder solution, the solute is the sugar and the solvent is water. So in this one, you have a mixture known as what we would just call sugar water. Okay, so the sugar is being dissolved in the water. So sugar is the solute, water is the solvent. Now, there are different types of solutions. Solutions can be made up of different combinations of solids, liquids, and gases, as shown in this table. Let's take a look at some of the items in this table. The Earth's atmosphere, okay? The solvent, all right, would be nitrogen, which is a gas. And then the solute would be oxygen gas, carbon dioxide, which is a gas, and argon. So all of these gases would be dissolved into the nitrogen in order to make Earth's atmosphere, which is a gas. So this particular solution right here is a solution that just consists of substances that are at the gas state, okay? You can also have solutions like ocean water, which is very similar to salt water. That would be water being your solvent, which is a liquid, and then something like salt, which is a solid, that's your solute, as well as oxygen and carbon dioxide gases are found in ocean water as well. So this one would be like a liquid solid gas type solution. And then of course the state of the solution is a liquid. So this right here, you can see that there's all different types of solutions. You don't just make solutions using, a lot of times we may think that it's just maybe some type of liquid with some type of solid. There's all different types of ways to make solutions. Solutions can contain solids and liquids, liquids and gases. It's just a combination of different ways that you can make solutions. And this is a really good table that gives you some good examples of some common solutions that we have heard of. Okay. Now that we've talked about how solutions are made, let's talk a little bit about properties of solutions. There are three specific properties that we're going to look at on this particular slide. First, let's talk about the solute versus the solvent, which we kind of talked about on the previous slide, but we'll just kind of rephrase that here. Solutions are made up of a solvent and a solute, and that's something that all solutions have in common. The solvent is the substance that does the dissolving, and the solute is the substance that gets dissolved. Okay. Concentration. Solutions can also be associated with a concentration level. The concentration of a solution tells you how much solute is present compared to the amount of solvent. Okay. So you can give a simple description of a solution's concentration by calling it either concentrated or dilute. And you've probably heard these words before, especially on food items. A concentrated solution has more solute per given amount of solvent than a dilute solution. So the more concentrated your solution is, that means you've got more solute per given amount of solvent. Okay. A dilute solution, however, is going to have less solute per given amount of solvent. You can see that a lot of times on your food labels. If you look at this juice label, it says 100% pure Florida squeezed grapefruit juice. And sometimes that's how concentration may be presented to us, is as a percentage. And this just tells us that this is a pretty concentrated solution. When it says 100% pure, that means it's going to have more of that solute per given amount of solvent, which in this case, your solvent is probably going to be some water, okay, or some other type of substances that they're using to make this juice. But what this is telling me is that would be a more concentrated amount based off of the percentage that we see there. So when you think about concentration, let's just think about using the words concentrated or dilute. And the more concentrated something is, that means it's going to have more solute in it per given amount of solvent. Conductivity is another property that we can associate with solutions. Conductivity is the ability of a substance to allow electricity to flow through them. So solutions have that property. There are some solutions that will conduct electricity. In solutions, the electric current is carried by what we call our cations and anions. Now, if you think back to when we were talking about chemical bonding, you remember that an ionic bond will consist of a cation and an anion. This would be, remember, a cation is a positive ion and an anion is a negative ion. So ionic bonded substances, when placed in solution, tend to be the ones that are going to cause that solution to carry electric current. For example, if I look at water, okay, water is a covalently bonded substance. So water by itself is not going to conduct electricity. But if I mix that water in the presence of some type of ionic bond, such as salt, for example, then that will conduct electricity. And remember, we did have this discussion when we were talking about ionic versus covalent bonding. We learned that ionic bonded substances are conductive, that they will conduct electricity. So this kind of brings that all together when we're talking about this as being a property of solutions. Okay, solutions that are there are solutions, excuse me, that will conduct electricity, and typically the solution is going to contain some type of ionically bonded substance. Okay. Now, let's talk about the rates of dissolving, because not all solutions are going, the solute is not going to dissolve all at the same rate. There are some different factors that are going to affect how fast a solute will dissolve in a solvent, and they are temperature, surface area, and agitation. These are all factors that are going to affect how quickly a solute is going to dissolve in a specific solvent. Okay. Agitation. A solute dissolves faster when the solution is stirred or shaken. So look at this picture here. Okay. This one here, you've got some acid particles mixed in with some marble chips. Now, when it's not stirred, you can kind of see the marble chips are kind of sitting at the bottom of the container here. However, if you stir it or agitate it or shake it or anything in that way, then what you do is you speed up the rate at which this solute is going to dissolve. What is happening is that you're exposing more surface area of the solute to the solvent, therefore speeding up that process of it being able to dissolve. So this is a way that you can speed up the process of making a solution if you stir it or shake it, okay, which is what we refer to as agitation. Temperature is another factor that will affect how quickly a solute is going to dissolve. When the temperature of a solvent increases, the solute will dissolve faster to make the solution. For example, if I'm trying to dissolve sugar, sugar is going to dissolve a whole lot quicker in hot water than it would in cold water. Okay, so increasing the temperature will also increase the rate of dissolving for a solute. Our last factor that affects the rate of dissolving is surface area. Okay. When you increase the area of contact between the solute and the solvent, you can increase the rate of dissolving. This can be done by breaking the solute into smaller pieces, which increases the surface area of the solute that is exposed to the solvent. So, for example, if I wanted to dissolve sugar in water and I have sugar cubes versus my ground up sugar, this sugar is going to dissolve much faster because you are exposing more of its surface area to the solvent versus if I have the sugar is bound up into a cube. Okay, so this one right here is going to dissolve a little bit slower than this particular form of sugar. Okay, all right, now our last part of our video lesson is we're going to talk about a solubility graph. Let's take a look at what that shows us. All right, on this solubility graph, first of all, it is showing us the amount of substance that will dissolve in a particular, will dissolve in solution at particular temperatures. Okay, so let's go back up here and look at some of the background information about this graph. First of all, solubility is a measurement that describes how much solute will dissolve in a given amount of solvent. So when you're talking about the solubility of something, you're measuring how much of my solute is going to dissolve in this given amount of solvent. The solubility of some solutes changes as the temperature of the solvent increases. So solubility graphs are used to show this relationship between the temperature and the solubility. So let's take a look at this graph below because it shows us how the temperature of the solvent affects the solubility of some solutes. And we're looking at the amount, how much we're putting in there compared to the temperature of the solvent. So for example, let's look at a line on this graph. According to this graph, is it likely that warm ocean water contains any more sodium chloride than cold ocean water does? Well, let's find the line that represents our salt water, because that's what ocean water is mainly a solution of. So if we look at this, it's the blue line. And if you look at this line, it's pretty horizontal. So no matter whether you have warm ocean water or if you have cold ocean water, um, it's not really going to change the. So from this graph, we can see that when you're using, and if you look here, if we have about 40 grams of salt and you increase the temperature of this solution, it's not really going to contain more sodium chloride than it would if it was a lower temperature. Versus if you're looking at sugar, the more sugar you add, the more you can dissolve at higher temperatures, the more that it's going to dissolve at the higher temperatures. Because this graph, as you can see, has a curve here, okay? So basically what I can see is that with the sugar, more sugar is going to dissolve at your higher temperatures versus salt. If you have cold ocean water versus hot ocean water, you're going to have about the same amount of sodium chloride in there. So this graph really shows us the amount of solute that we're dissolving in our solvent and the given temperatures. So we can kind of see how changing the temperature is going to affect the amount of solute that will dissolve in a particular solution. We have now reached the end of our video lesson. Please make sure that you have adequate notes recorded and rewatch the video if needed.